Okay, so let's look at problem 410. Split array largest sum. So here we are going to share a binary search idea or solution to this problem. So first, I will go through the statement of the problem, and then we look at the constraints, and then we look at the method and the specific procedure. And finally, we work together to write the code, and then we test the generic case and do a rough time complexity analysis. So let's look at the statement of the problem first. So given an array called nums, so which consists of non-negative integers and an integer m, so we can split the array into m non-empty contiguous subarrays. So the problem asks to write an algorithm to minimize the largest sum among these m subarrays. So that's the main statement. So let's look at these examples. So in example 1, m equals 2, so the output is 18. So this is a split. So this two subarray, and this has some 14, and this has some 18. So the larger is 18. So the cap m is 18. So in example 2, so the output is 9. So one split corresponding to this is 1, 2, 3, and 4, 5. So 1, 2, 3 has some 6, and 4, 5 has some 9. So 6 and 9, the larger is 9. So the output is 9. So we cannot do other partitions. For example, if we partition this one as 1, 2 as 1, and 3, 5, 4 as another one. So the larger will be 3 plus 9 plus 4 plus 5, that is 12, right? So we cannot make it too screwed, in other words. So in example 3, so this is a special case. The m equals the length of nums. So we need to split these nums into 3 subarrays. So the maximum of the sums will be 4, right? So that's the return. So let's look at the constraint. So the length of the nums, first is not empty, and then it's bounded above by 1000. And the range of a generic element in nums is non-negative and bounded above by 10 to the power 6. And the last constraint is on m. So m is greater or equal than 1 and less or equal than the minimum of 15 as the length of nums. So with this statement went over, let's look at the method and the procedure. We'll come back to the constraint again after we finish the code. So here the method or the idea we're going to use is again binary search. So this is not the vanilla binary search like we search an element in a sorted list. So basically this method has the following two steps here in its scope. First, we define a boolean function to produce order or monotonicity. So this is the key, and this is also the elegant part for using binary search in such a scope. Second, so based on the boolean function defined above, so we transform the problem to a minimization or maximization optimization problem. Then we do the shrinkage on proper search space. So in other words, in the process, we need also try to determine a better or proper search space. We'll see this. So note that here we will transform the problem to a minimization problem. So before we look at the code together, so here is a challenge. So can you identify a problem in Leetcode that can be transformed to a maximization problem and then solved by binary search? So with that said, let's look at the code together. So basically I will run the 2 steps I mentioned before. So step 1, so basically define the boolean function to make preparations for doing binary search or doing the shrinkage. So here the function basically is such that if we could guarantee that if we split the array into m consecutive subarrays, each sum and every sum of the subarray is less or equal than k. K is the argument we are going to specify, we are used in the function. So I'll call this function fulfill. This is easy, right? So if k is very large, basically we can do this, right? So basically for this, I'm going to initialize a count, and also we want to initialize a running sum. I want to count if I use a cap as k. If I want each of the subarray has sum less or equal than k, will the number exceed m or not, right? So then once we realize this thought, we can iterate for the numbers. So for y in nums, what we want to do is that we check if x plus y is greater than this cap k. If so, we cannot put the current y in the previous subarray. So we just increment the number of subarray by 1 and reset s to be the y. So this is the one step. Otherwise, so if s plus y is less or equal than k, so we can actually increment this s by y, right? In other words, we can still put the current y in the previous subarray, right? So then if we do this, after the for loop, because we want to notice that at the last index, we make a comparison again. We want to check if s is less or equal than k. Then we want to update the count by 1. So basically the thing is that we want to check if this count is less or equal than m, right? So if given such k, the count is less or equal than m, it means that we can do the partition. So with that said, we are ready to go to step 2. Step 2 basically do binary search. So in order to do binary search, so first we need to transform the problem and then identify the proper search space. So the question now is transformed to that we want to find min k, minimum of the sums, such that the fulfill k is true, right? So once we transformed into such a form, we can easily identify that it's a binary search problem. So now we want to determine the search space. So determining the search space is not a trivial thing. So here I would say the lower bound will be the maximum of nums. The reason is that the maximum of nums must be contained in a subarray. So that subarray must have sum greater or equal than the maximum of numbers, right? So that's the reasoning behind. And the upper, so the upper actually is the sum of nums. So we can think of the special case m equals 1. So when m equals 1, so the cap actually is the sum of nums. So for the lower bound, we cannot shrink it anymore. But for the upper bound, so because the larger the better for the cap, so we can still increase that, but it's not sharp. So I would say again, so if we define lower as max of nums and upper as sum of nums, so this lower and upper bound for the search space is sharp. So with that said, basically I would do the binary search. So then I will initialize them, lower and upper, basically it's maximum of nums, and sum of nums. Then what I want to do is that I want to check if lower is less than upper. If so, I'm going to increment, I want to define the middle. So the middle is basically the half of the range. So basically, if we use lower as a reference point, it will be upper lower plus upper minus lower divided by 2. So here we use integer division. Then what we want to do is that we check if fulfill and mid is true. If this is true, then we actually see that the search space will be from lower to mid, right? Inclusive. Because of inclusive, we are going to reset the upper to mid, right? Otherwise, so mid does not return true for fulfill, then the search range will be strictly greater than mid and then to the upper. So we want to set the lower to be mid plus 1. Plus 1 because mid actually is not okay. So with that said, if we interpret the meaning, we are going to return the lower. So that's the whole procedure. With that said, I would say let's first check the special examples, and then we check generic case, then do the time complexity analysis. Yeah, it passes example 1, and now let's look at example 2. So m equals 2, because for this one we know how to split 1, 2, 3, and 4, 5. The return should be none, right? Then for the special case or edge case, I would say, so what we have will be 4, right? Which is the maximum of this one. So yeah, so it passes this case. Let's submit for generic case. It passes the generic case. So here, let me review this procedure and emphasize some point again. So here, actually, we can use an early stop condition. So if count is greater than m, so we can actually return false. So here, we can, if count is greater than m, so just return false. So we can add 1 here, but this is just one step. So we do not add this last index. So you can check that. So it passes. Another thing is that about the search space. So this search space is sharp, right? So, but if you add something to the upper, so yeah, it's still okay. But you know, let's add 10. So it's still okay, but you use more time. So, but you cannot shrink the this lower bound, because if you shrink which is less than the maximum of numbers, so that specific maximum cannot be distributed, right? So let's keep the sharp one. Then let's do as an extra point, let's do a estimate, so our time complexity analysis, so to speak. So basically, here we call the fulfill function in this range. The search range is basically the sum of nums minus maximum of nums. And then because we do binary search, so we search such number of times, log 2, right? So for each times we are going to use this fulfill function. So basically it's a linear function. So it's an O of the length of the nums, so it's nums. So then if we look at the constraint here, so actually we can do a rough estimate, so which is less than log 2 the sum of nums. So the sum, it can be less than, because each has largest range is 10 to the power 6, then times the length can be 1000. So that's it. So minus something, just let's drop that. Then times the length. The length is roughly 1000. So we will do this computations up to a constant. So we will do this will be less equal. Okay, so log 2, so 10 to the power 9 times 1000, right? So this basically this is 9 times log 210 times 1000. So this 1000 is the length, right? This 9 is the scale. So roughly 9000 times log 210. But if you like, you can estimate say log 2. Log 2 is log 210 is less than 4, right? Because 2 to the power 4 is 16, so it's less than this number. So yeah, so we'll say it's the algorithm time complexity is this number, right? So if you want to be more precise, so we can get this number. So with that said, I would say for this problem, that's it. So we will practice more about this line of ideas in later videos. Thank you very much.